Como sabrán, este es nuestro primer Congreso Internacional de Ingeniería Geotécnica. Es la primera ponencia del día de hoy, así que estamos abriendo con broche de oro, estimados compañeros. La estructura va a ser que primero vamos a presentar al equipo GeoUPC, qué somos, quiénes somos y por qué lo hacemos. Vamos a conocer un poco más a la doctora Gertraud Medicus, que es de nacionalidad austriaca. Va a exponer su tema de Animating Soil Model Visualization a Staging and Learning Material for Soil Constitutive Modeling. Y al final de la sesión habrá una ronda de preguntas del público asistente. Ok, ¿quién es o qué es GeoUPC? Somos un equipo conformado por alumnos de la carrera de Ingeniería Civil de la Universidad Peruana de Ciencias Aplicadas, UPC, y tenemos como razón de ser nuestra formación como profesionales en el ámbito de la geotecnia. Nosotros conformamos un espacio crítico y de investigación donde participamos y creamos actividades para la comunidad estudiantil con el objetivo de promover y fomentar nuestro desarrollo personal y profesional para poder llevar todo lo aprendido de manera teórica a la práctica. ¿Ok? Conozcamos un poco más a la doctora Gertraud Medicus, quien está tocando el tópico de modelamiento numérico con su tema Animation Soil Model. La ingeniera Gertrudis es ingeniera civil de la Universidad de Innsbruck, Austria, y por la NTNU de Trondheim, que están en Noruega. Es doctora en ciencias de la ingeniería, con honores por la Universidad de Innsbruck, Austria. Tiene una tesis doctoral, Biodiversity and its Application to Clays. Es ingeniera geotécnica especialista en mecánica de suelos computacionales. Realiza investigaciones sobre modelos constitutivos, particularmente utilizando el marco de la hipoplasticidad, Biodiversity Framework. Tiene como objetivo contribuir a la comprensión del modelamiento geomecánico de suelos mediante el desarrollo, la aplicación y enseñanza de modelos constitutivos, realizó postdoctorados en diferentes proyectos hasta 2017 y de 2017 hasta la actualidad es la IP del proyecto independiente de FWF, Riding in Biodiversity. En 2022 ocupó el puesto de Elise Richard de la FWF. Tiene con el título de Ensayo de suelos como problemas de valor límite. Bueno, no les quito más el tiempo, le voy a dar el pase a mi compañera, la ingeniera Shirley Suárez, para que pueda seguir con la presentación en inglés. Gracias.
Thank you, Sandro. Dr. Medicus, and let's talk about your experience, just to know about the audience. And welcome once again, and we are very pleased to come with your presence today, and we'd like to thank you in advance for letting us know to learn from you at this topic. Okay, as you may know, when a civil engineer from the University of Innsbruck in Austria, and from the NTNU in Trondheim, Norway. You have a doctorate in engineering science with honors from the University of Innsbruck in Austria too in 2014. You have a doctoral thesis, Biodiversity and its application to clays. Also, it's known as geotechnical engineer, it's specialized in computational soils mechanics. And nowadays you conduct research on constitutive models, particularly using the Biodiversity framework, which objective is to contribute to understanding the geomechanical modeling of soils for development, application, and teaching of constitutive models. You did your postdoctorate in different projects until 2017. And from that to nowadays, you was the IP from the WF independent project Reloading in Biodiversity. And in this year, you held the WF Elise Richard position, so testing as limit value problems. So you have a long experience, and we are very pleased to come with this. And now that we have talked about your experience, now you can share your screen just to.
Perfect. Thank you.
Slides.
Thank you very much for your introduction, and also thank you very much for your invitation. As I said before, it's my first time to be virtually in Peru. I've never been there in person, so it's very nice to start with this visit today. I will now talk about how visualizations and animations can help to understand soil constitutive modeling. And doing that, I will present a project called Animating Soil Models, which includes a lot of visualizations. Before I will, oh, there's something wrong. Before I will start showing the visualizations, I will give a short introduction to the topic. Why do we need constitutive models, and why do we need to understand them? Everyone needs a constitutive model if the person carries out a finite element simulation, and we have to choose an appropriate model, and we have to, this is a bit too quick, but yeah, we will see. We have to, it works better like this. We have to interpret the results, and therefore we have to understand the constitutive model. In addition, constitutive models include a lot of theories from soil mechanics, or which include mechanical, soil mechanical, and also mathematical concepts. And to understand these concepts can also help to understand and explain soil mechanics. And these models are therefore also frameworks which provide the possibility for further understanding. There are many different ways how probably every one of you and myself learned constitutive models, and or how we teach them. We carry out computations, we need explanations, and we need discussions. There are fantastic books about the topic, and of course there are videos and also courses at university. And probably there's a lot more. I will not talk about all that. I will just present one detail on how you can teach or learn constitutive models, but all the above mentioned points are definitely very important. And yeah, that's what I said in the introduction. I will talk about the visualizations as one possibility to improve the visual aspect of teaching and learning soil constitutive modeling. Within this project, there are different topics that I visualize. There is quite a large part on failure surfaces. I visualize different models, elastoplastic and hypoplastic models. And in this presentation, I will pick some of those visualizations and make some comments. And I hope in the audience there will be some who still can learn something, and I also hope that there will be some lecturers who get an overview what is in this project, because the whole idea of this project is that I didn't make this for myself. I also made these things for my teaching, but the whole idea is to share this content with everyone. So you can go on the project's website and just download, use, do whatever you want with those animations. And yeah, if you find them helpful. And they're shared under this open CC BY license with everyone. I will now give a short introduction on stress measures and stress invariance. In the whole presentation, I consider stress as positive in compression. And if we want to characterize a certain stress state in geotechnical problems, we often use principal stresses. And if we then as well consider axisymmetric stress states, it's sufficient to just use the mean effective stress and the deviatoric stress to describe a stress state. We will quite often see this red line in PQ plane in the following slides. This is, for example, the Mot-Coulomb failure line for zero cohesion. And I will now show a stress path of a drain triaxial test. It starts at a certain consolidation pressure and has a certain inclination and approaches and finally reaches this failure surface, in this case for a loose sample. If I continue to consider principal stresses, then we can display a certain stress state that can be this red bullet here on this Mot-Coulomb hexagon. We can display this certain stress state in principal stress state. This animation or this figure includes the hydrostatic axis, the blue line, and the hydrostatic axis includes the current mean effective stress of a certain stress state, and the distance of our red bullet to the hydrostatic axis can be characterized through the deviatoric stress. And to now we also need a third stress measure in order to define the state of this rest stress state here displayed. I now rotate this whole plot into the deviatoric plane. And that can be the loader angle. And in this presentation, I use the following definitions. There are more definitions to be found in literature. For axisymmetric triaxial compression, I use 30 degrees, and for extension states, I use -30 degrees. And yeah, so that's what we can see here. A disadvantage of those animations is that I decide where you have to look, and you can adjust the speed if it's too slow or if it's too quick. That can be done, at least in the PDF version, PDF animations by yourself. But sometimes it would be probably more convenient if you could choose where to look at, and therefore also created some other interactive plots where you can rotate the Mont-Coulomb hexagon yourself. You can have a look in the deviatoric plane. I added cohesion to the Mont-Coulomb hexagon that results in a shift into the tension regime, and you can also rotate it and zoom. Adding a cohesion to, in this case, the Mont-Coulomb hexagon allows certain tensile stresses, and that means that plane stress predictions are possible for cohesive material. And here, where the transparent part meets the solid part of the hexagon, that's how plane stress predictions look like for Mont-Coulomb failure. And in this plot, I also added a scaled PQ plane for axisymmetric compression to the principal stress space, and you can, if you want, rotate it, the whole thing into PQ plane, that you get a feeling for these different planes you can find in literature, the deviatoric plane, PQ plane, and so on. I also, if you're interested, you can find all that on the web page, but if you're interested in this PDF handout of my presentation, I have all those visualizations linked. I send it to the organizers, so you can have the PDF later if you want. Those yield surfaces I just showed and those yield surfaces which are on this slide have been created with a open available software called Asymptote. And this is, I learned this software within this project, and I can highly recommend it for 3D plots. And I also uploaded some example script on that page because it just makes a very nice rendering, and it's highly recommended. You can also find other failure surfaces like the Fomesis failure surface, and you can also have a look. You can have a look how do plane stress predictions look like von Mises in comparison to Mont-Coulomb, what we saw before, and I'm gonna close that now because I don't need that anymore, and also don't need Mont-Coulomb anymore. So where did I put my? Maybe I just close the presentation. I'm just lost. Oh no, here it is. Another failure surface, also sometimes used for undrained strengths in solid mechanics, is Tresca. Again, you can find interactive graphics where you can have a look at. There's another surface according to the Drucker-Prager cone. I want to show another interactive plot because it's a bit different to the one I showed before. And before I will talk about Drucker-Prager, I will again talk about the principal stress space. Here on the left side, you have the principal stress space on the left side. On the right side, you can see the deviatoric plane, and the red bullet is your current stress state. And you can play with this stress state and choose the stress state you want, and you can look at your principal stress state here in the middle. And on the right, you can find the corresponding stress invariance, mean effective stress, deviatoric stress, and the loader angle. And you can play a bit with that. In addition to that, you can add the Drucker-Prager cone here, and you can decrease or increase the opening of the Drucker-Prager cone. And this plot should help to get a feeling for stress invariance, for the deviatoric plane, and also for principal stress space. Another failure surface, I will continue to talk about that a bit later, which is included in some constitutive models like clay and sand hypoplasticity, is Matsuoka-Nakai. It doesn't look like Mont Coulomb because it's more round, but it also doesn't have a circular in the deviatoric plane. It's not a circle, so it's different to Drucker-Prager, what we saw before. And we can again have a look on Matsuoka-Nakai. How does that look in the deviatoric plane? How do, for example, plane stress predictions look in the case of Drucker-Prager, and so on. If we compare Matsuoka-Nakai with Drucker-Prager for a certain mean effective stress here in the deviatoric plane, here on the left we can see the deviatoric plane, and on the right hand side we compare mobilized friction angles of the different failure surfaces. In red we see Matsuoka-Nakai, in blue we can see Mont Coulomb. And what we can see here is, at least for zero cohesion, the predictions coincide for axisymmetric extension and for axisymmetric compression. But in between, for the same parameters, strength predictions are a bit higher for Matsuoka-Nakai than they are for Mont Coulomb. And the difference is highest, about around 15–16%. Somewhere between compression and extension. And that's the range of loader angles, somewhere between 0 and 15 degrees, where plane strain failure is reported to occur. So that's a range which is definitely relevant in finite element simulations, because we often model or idealize a problem under plane strain conditions. In this plot, I show the normalized deviatoric plane, and I added some experimental data that is available of normally failure points of normally consolidated San Francisco Bay melt samples, and we can see that they scatter a bit, but they can be better described by Matsuoka-Nakai than by Mont Coulomb. In this plot, I again show the PQ plane and the failure line according to Moore-Coulomb or Matsuoka-Nakai for axisymmetric triaxial compression for zero cohesion. It's quite obvious what will happen if I increase the cohesion and reduce the friction angle. Probably no one is very much surprised that we increase strength for low stresses and we decrease strength for higher stresses than 100 kilopascal. I will now continue the same, but I added the deviatoric planes and I do exactly the same. I keep 100 kilopascal, the axisymmetric stress state, I keep that fixed in all three plots. And in the middle, I show Matsuoka-Nakai for a mean effective stress of 100 kilopascal. And on the right, I show Moore-Coulomb for a mean effective stress of 100 kilopascal. And then I again change parameter and we will see what happens. And it's interesting to see that even though we keep the axisymmetric stress state fixed, by changing the parameters, strength prediction of every other deviatoric direction changes. And eventually, for zero friction and a certain number value of cohesion, Matsuoka-Nakai will turn into mesas, what we saw before, the cylindric shape. And Moore-Coulomb will eventually become, for zero friction, will become Tresca. So we have to keep in mind changing friction angle and adding cohesion will change the shape of a failure surface in the deviatoric plane, even though for a certain stress state for axisymmetric compression, there's no change in strength predictions. So far, I haven't talked about models, just about failure surfaces, and I will again show what I showed on the first slides. Here above left, I show PQ plane with, let's say, Moore-Coulomb failure line for zero cohesion and a stress path for an initially loose Hoster sand sample. I show the predictions with a linear elastic, perfectly plastic model with a failure surface according to Moore-Coulomb. We see the predictions have a certain stiffness at the beginning and then zero stiffness when Moore-Coulomb failure line is reached. If I increase the stress level, we can see that by increasing the stress level, the strength increases. It's proportional to the stress level. But we can also see that the stiffness in this model is not increased compared with the lower mean effective stress. And we can basically see what we saw before. By further increasing the stress level, strength is increased, but stiffness is kept the same. And if I add here laboratory test result of, again, an initially loose Hoster sand sample, but this time for a consolidation pressure of 300 kilopascal, we see strength is increased and it's quite well predicted by the model, but the stiffness should also be increased for higher stress levels, and that's not captured by this model. There are some variation also on the website where Poisson ratio is varied, and I show one. I will now show one on this slide. I again choose the initially loose sample and show predictions with a Poisson ratio of 0.05. I increase Poisson ratio and we can see that in this case, only the volumetric response is affected and not the deviatoric stress and in this case, axial strain curve. For other tests, such as an odometric compression test where lateral expansion is hindered, or also a plane strain biaxial test where one direction is hindered, the Poisson ratio also affects the stress path and not only the volumetric response. I will now talk about models that are related to critical state soil mechanics. That is, in this presentation, the modified chem-clay model and clay hypoplasticity. Again, on the left side, we can see PQ plane. We can see a critical state line in stress plane. And there is some bounding line. I will talk about that a bit later. What is important in critical state soil mechanics is that there is a critical state line not only in PQ plane, but also in void ratio mean effective stress plane. It's the red line here on the right side. And there is also a normal compression line which characterizes normally consolidated states of clay. The critical state line in void ratio mean effective stress plane helps to distinguish between normally to slightly over-consolidated soil if the void ratio is larger than the critical void ratio, and if the void ratio is smaller than the critical void ratio, we have highly over-consolidated clay. And if we translate that to sand language, it's loose sand, or if the void ratio is smaller than the critical one, it's dense sand. Here in 1+ void ratio mean effective stress plane, we can see wheeled clay data of endpoints of undrained triaxial tests of normally and over-consolidated clay. And we can see that these endpoints of undrained tests, they can be well described or well fitted by a line, and that is the critical state line. And if we plot this line in a logarithmic plot, we can see that all those data points and lie on a straight line, and that's the critical state line that is often assumed to be parallel to the normal compression line in critical state soil mechanics. I will now show some animations of an elastoplastic model, the modified chem-clay model, and I will start with a simulation of a initially normally consolidated drained triaxial test. On the left side above, again, we see what we saw before, the critical state line in PQ plane. We can also now see in gray a yield surface, and in the modified chem-clay model, the yield surface has an elliptical shape. And we will see the directions of plastic, or we will soon see plastic strain increments, but I will talk about that when the animation starts. Below, we can see what I explained before. We can see the critical state line in void ratio mean effective stress plane and a normal compression line. And above right, we will see a stress strain curve, deviatoric stress plotted over deviatoric strain, and below we will see the volumetric response of a trained triaxial test. As I said before, the sample is initially normally consolidated. That means that the initial state is on a normal compression line. And for the yield surface, that means that my maximum pre-consolidation pressure coincides with my current initial mean effective stress. Now that the simulation started, we can see the stress path in PQ plane, and the model includes associated flow. That means that the direction of plastic strain, that's the green arrow here, is perpendicular to the yield surface, to the gray elliptic failure surface. And as we continue to shear, we can see that the ratio of volumetric strain increment to deviatoric strain increment decreases, and that means that eventually when we approach and when we finally reach critical state, we just have ongoing deviatoric strain and no longer any change in volumetric behavior. And we have reached critical state here in void ratio mean effective stress plane and here in PQ plane. And we can see that there's no more further change in volume. And yeah, that's critical state. I will now show again a simulation of a drained triaxial test with a modified ChemClay model, but this time of an initially highly overconsolidated state. Highly overconsolidated means that the pre-consolidation pressure of this clay has been a lot larger than the current initial stress state. And the current initial stress state is in PQ plane, this blue or black bullet. And the overconsolidation pressure defines the size of the yield locus. And we can see that is now a lot larger than it was before for the normally consolidated sample. And highly overconsolidated initial state also means that the current void ratio is smaller than the critical void ratio. And that means it lies below the critical state line. We will now just look what will happen if we start the simulation. The stress path is now within the yield surface. That means that the initial response is elastic. As the sample is highly overconsolidated, we can this time exceed the critical state line until we reach the yield locus. And then we can see that softening occurs. And what we can see in the void ratio mean effective stress plane is we had compaction at the beginning, but now the sample has to dilate in order to reach critical state. And we can see in the deviatoric strain curve, we can see the softening behavior until we reach the critical state line. And we can again see a dilative behavior, and we can see that approaching critical state, the volumetric strain increment, the ratio of the volumetric strain increment to the deviatoric strain increment reduces. And finally, we just have ongoing distortional strain and no change in volume. I will continue with undrained compression tests of, again, a normally consolidated sample. I again show the same plots. I just added another line. The dotted line above left is the total, indicates the total stress path. And I exchanged the volumetric response with a pore pressure development, because the volume in an undrained compression test, it stays constant, and therefore it wouldn't be interesting. We can see, oh, we have to wait a bit. The difference between the current stress state and the total stress path defines the pore pressure. We can see for the initially normal consolidated state, we can see that pore pressure increases until we reach critical state. We can see typical for normally consolidated clay, the stress path that goes to the left. And we can see a stress strain behavior that looks similar to the one of the drained triaxial test. And again, we reach critical state. We have no more change in pore pressure. We have reached critical state in void ratio mean effective stress plane, in PQ plane, and the volume was kept constant throughout the whole simulation. I will now show a simulation of an undrained test, this time not of highly overconsolidated clay, but just slightly overconsolidated clay. That means that the initial state in void ratio mean effective stress plane is just in between the normal compression line and critical state line. We therefore have a bit of an elastic response until we will reach the yield locus. And again, we have an increase in pore pressure. Maybe we can speed up a bit. And elastic response means within a model that the mean effective stress stays constant in the elastic regime. And then we can see, very similar to what we saw for the normally consolidated clay, a very similar response, except for the very beginning until the yield surface is reached. And a bit different, again, an undrained Drexel test of highly overconsolidated clay. This time, the initial response, the elastic response, so speed up a bit, we can see that the mean effective stress in the elastic regime stays constant. And then when we reach the yield surface, we can see that the yield locus shrinks, and we have a decrease in pore pressure. And when we reach critical state, there's no more change in pore pressure. The critical state line is reached in PQ plane and in void ratio mean effective stress plane. And due to the shrinking of the yield locus when yielding, that explains the different stress strain curve in Q epsilon Q plot. There are the parameters you need to calibrate the modified ChemClay model are the friction angle to define the slope of the critical state line. It's sometimes, the slope is sometimes called M. You have a ordinate intercept of the normal compression line. You have a slope of the normal compression line and also of the critical state line. You have a slope of an unloading line, and you have to define shear stiffness. I will now show some interactive plots that are related to the modified ChemClay model. Basically, you have seen this quite a couple of times now. It's PQ plane. The blue line is the hydrostatic axis or the normal compression line, and the red line is the critical state line. And here I show all parameters of the modified ChemClay model, and you can play with those parameters and see what happens. And if you increase friction, you have a different slope, and that affects the critical state line in the projection in PQ plane. And all the other parameters, they don't change anything in this plot. But you can rotate this plot. You can have a look, yeah, it's a three-dimensional plot, but you can also have a look in the void ratio mean effective stress projection and see how the parameters affect this projection. The critical friction angle, or M, doesn't change anything, but the slope of the unloading line slightly changes the critical state line. The slope of the in the semi-logarithmic plot of the normal compression line and critical state line changes the normal compression line and critical state line, and you have the ordinate intercept that also changes both. And I think this plot can help to understand that those two lines, they are three-dimensional lines, and it's sometimes very convenient to rotate in the projections you're interested in. And you can also add the state boundary surface with the elliptic shape in PQ plane, what we saw before. And you can add a certain pre-consolidation pressure and have a look on this gray yield surface and play a bit if you want. It's another open software I used, and it's free for everyone. It's called GeoUPC. It's also a lot used in schools for teaching math. It's quite, the rendering, it's not as nice as with this asymptote program software, but what is very convenient with this software is that you can easily create those sliders, and that's, I also can highly recommend this software. And here is basically the same, but you cannot change the parameters, but you can have a look at the different projections in void ratio mean effective stress plane and so on. We have for the simulations of the modified chemical model, I just talked about axisymmetric states, but here I show the state boundary surface in a principal stress space with a deviate. There are different possibilities, but this one is has a circular shape in the deviatoric plane, and you can have a look at this ellipsoid, how this looks in principal stress state as well. I will now talk a bit about a different model called clay hypoplasticity. The math between this hypoplastic model and the modified chemical models, the equations, they differ quite a lot. But the concepts behind, you're very familiar with those as well, because you can see them already. You can see the critical state line in PQ plane and in void ratio mean effective stress plane. You can also see that the response for this initially loose sample is quite similar to what we saw for the modified chemical model. I again show this similar planes, but I also, in this case, I added the ratio of deviatoric stress to mean effective stress state. I will now keep the void ratio, the initial void ratio constant, but reduce the initial consolidation pressure, and we will see what happens. Not a lot in this case for the slightly over-consolidated sample, but we can see that strength decreases because we decrease the initial mean effective stress. If we further decrease the initial stress level, we can basically see what we saw before. And when this initial state becomes highly over-consolidated, we can see that the stress path can exceed the critical state line. We can see a peak and softening in the stress strain curve. We can see that the ratio of deviatoric stress to mean effective stress can exceed the critical value, and we can also see compaction and a bit of dilation. And if we further increase the initial over-consolidation, we can see that this behavior is even more pronounced. One difference to the modified chemical model is that the stress strain curve for highly over-consolidated clay and also for slightly over-consolidated clay, it's smooth. And that's maybe a difference, but the concepts are very similar. I will now again show simulations of drain Traxel test with the clay hypoplastic model, but this time I will keep the mean effective stress constant, the consolidation pressure, but I will reduce the initial void ratio. We saw that the response of the normally consolidated clay before, and keeping the initial stress constant means that the critical strength will stay the same. And if we further decrease the void ratio, we will see that strength is increased, the stress ratio is increased, the critical void ratio as well as the critical strength is kept the same because the stress level is the same. And if we further increase the over-consolidation ratio or decrease the void ratio, we can see that the behavior becomes more pronounced. I will now show undrained Traxel tests of the model. And again, the initially normally consolidated response is very similar to the modified chemical model. And I will now keep the stress state again constant, but increase the over-consolidation ratio. And we can see that this affects the effective stress path of the undrained Traxel tests. We can see that the stress path of the highly over-consolidated sample, it can exceed the critical state line, and it becomes more pronounced for higher values of initial over-consolidation ratio. And Again, I will show simulations of undrained triaxial tests, and this time I will keep the void ratio constant, but we'll change the mean effective stress. And this results in the fact that what we saw before is that undrained strength is highly affected because we changed the initial void ratio. This time we will not change the initial void ratio, only the mean effective stress, and we will see that critical strength is not affected if we change the overconsolidation ratio. Just the stress path is affected, and pore pressure development, and also the maximum possible stress ratio. After the presentation, or whenever you want, you will have time to look at the things in more detail if you want. The parameters of clay hypoplasticity are very similar to the modified ChemClay model. There are some details, but again, we have the slope, the ordinate intercept of the normal compression line, the slope of the normal compression line, the slope of an unloading line, a critical friction angle, and a fifth value that affects the volumetric response, or also the shape of the stress path. Why is for the modified ChemClay model I used lambda, or not? It's not was not my idea. You always see lambda and kappa. For the clay hypoplasticity, you sometimes see lambda star and kappa star. That is related to the definition of the normal compression line and critical state line. In the modified ChemClay model, the definition is in a semi-logarithmic plot, and in the hypoplastic model, or for those models where you can see the star, or at least that's often the case, the normal compression line and the critical state line, they will become straight lines if they are plotted in a double logarithmic plot, if the mean effective stress and 1 plus void ratio is both plotted logarithmic, just a small difference. I will now, that looks very similar, just with, that's what I showed before. It's the state boundary surface of the modified ChemClay model. I have to probably reload it, just that we can maybe address some differences. We can see here an unloading line of the modified ChemClay model. That's what we saw before. And for clay hypoplasticity, I basically have the same plot. But we can see, maybe we can see it better if we plot. The shape is a bit different than for the modified ChemClay model. But basically, yeah, you can the bounding surface, yeah, maybe we see that better here. In the PQ plane, in the modified ChemClay model, this bounding surface has a strictly elliptic shape. In this case, it looks very similar, but it's a bit different. And there is a parameter where you can adjust peak states. So this is not strictly elliptic. You can change that if you're interested in. And in the principal stress space, I have not uploaded this plot because I'm not completely satisfied, but what we can see here is the transparent surface is related to the modified ChemClay model, and the yellow surface is related to clay hypoplasticity. And we can see differences in the deviatoric plane. It has a circular shape for the modified ChemClay model, and clay hypoplasticity includes Matsuoka Nakai in the deviatoric plane. And you can see that very well if it's overlapped, but you can also see that if you look individually on those figures, the clay hypoplastic model includes Matsuoka Nakai and the modified chem clay includes a circular shape, and it also allows certain tensile stresses. And in clay hypoplasticity, admission, the states are only restricted to compression regime. That's another difference of the models. I will continue to talk a bit about the project, and we'll also show the website. There are these 3D graphics that can include it in web pages. The animations I showed, you can simply download them as GIF animations, or you can also download them as PDF animations. The PDF animations have an advantage that you can take a break, you can adjust the speed. If you're not interested in the animations, you can just download all slides of an animation as PDF, and you can just include one slide in a presentation, or if you want. Where to find all that? There is a platform I highly recommend, not because of my project, but because of this platform. It's called Soil Models, and probably many of you know that platform. I'm going to close a bit of the rest in order to increase speed a bit. There is a platform, Soil Models, and on this platform you can download different, there's different software. There is simulation software. You can make simulations of using hyperplasticity. You can make simulations of drained and undrained compression tests yourself, and you can vary with the parameters. You can also calibrate your models, and you just need to have an account, but the account is for free. So if you log in and you have data, lab data, you can upload the data, and the software will calibrate the modified chem clay model and clay hypoplasticity. This has not done by myself, but by David Machine and his co-workers. You can also download different UMATs for finite element simulations, or DLL for Plaxis, if you want to use constitutive models for your finite element simulations, and not only for hypoplasticity. And among many other things, you find this project website. What I wanted to show, I haven't talked about it. There was a cooperation with the Madi Daibat from Canada, where we also did some visualizations of the Sunnysand plasticity. And you can in this case, you can see a Drucker Prager, which is anisotropic. I just talked about isotropic Drucker Prager before. And if you have an anisotropic cone, you need to define an axis in principal stress state. And in order to understand the model, it could help to play with all those values. You find also a short video that is related to Sunnysand plasticity. And you can also play with the parameters that affect the shape of the surfaces that are included in Sunnysand plasticity. What else to find? I also uploaded some MATLAB scripts in order to calculate and plot the different yield surfaces, for example, for Matzo, Kanakai, Mokolom, Drucker Prager, and also for this state boundary surface of the hypoplastic model. And I tried to add some comments to the script in order that they should be easy to follow, and you can just try them out and download them. What is the benefit of all that? I like to do that. I like to create visualizations that are related to constitutive modeling. But I also hope that there is a benefit for others as well. And it can help students. An animation creates a figure as an animated process, and that helps to follow a process. For example, it helps to understand the behavior in different planes at the same time. And if a point moves, it helps to find the right focus. So you will look at the line that will move, and you will not look at the other parts. But this is just an additional learning and teaching material. It certainly does not replace everything else, like studying what I mentioned at the beginning, studying the equations and the discussions, also doing computations and the books. But I hope that they can facilitate teaching and learning and understanding the concepts that are related to constitutive modeling. I'm finished with my presentation, but I just want to, before I'm certainly available for discussions, in this handout, I also added some further examples that are related to this, that have not been done by myself, but there are so many other useful examples that can help understanding and teaching constitutive modeling. And if you have a look on the handout, you can just have a look in general on this Soil Models webpage, on this calibration tool. There is a YouTube channel I can highly recommend, and there are other interactive visualizations that have been done by others and that are hopefully very helpful for you as well. Yeah, I'm open for discussion. If somebody has questions, I will be happy, or at least try to answer them, and I will be happy about that. Yeah, thank you for your attention.
Muchas gracias, Doctora Medicus. Thank you very much for the presentation. We think it's a very interesting topic, and I'm sure that the audience enjoy and learn it a lot thanks to you. We will give a space for questions from the audience. This is my...
Yeah.
The questions is Shirley. Go.
Yes, Dr. Medicus. Thank you so much for this big presentation. This exceeded our expectations. So now we can pass to the question and answer section. To you, I'm gonna say it, and you are about to respond.
Perfect.
Right. Okay, we start with this. This one is the first. What do you think advanced constitutive models, such as those based on hypoplasticity or bounded surface, are seldom implemented and used in practice?
If I recommend to use them in practice? Or what is the question? Sorry.
Okay, don't worry. I'm gonna repeat it. Why do you think advanced constitutive models, such as those based on hypoplasticity or bounded surface, are seldom implemented and used in practice?
Why did it? Oh, I don't know why they are not used in practice, but I think that we can all help to use them and to advertise them. And I think this platform soil models, which was initiated by some people, it helped to use those advanced constitutive models, because you can download the model. In practice, no one will, or no one, but hardly anyone will implement the models him or herself. So it's very convenient if you can download them. And I think it's also very convenient if you have a calibration tool, because you don't have that much time in practice. So I hope this is just a question of time, and those advanced models will be used more in the future. And together with the two colleagues, we also handed in it's a research proposal where we work with industry. We don't know if we will get it, but we want to work with industry, or we applied together with the industry partner to use those models in industry. So we will hope that we will get this project, because this would be one small step, but I think there is an interest in using those models. But I have never worked in industry, so I'm probably not the right person to answer. I don't know, but I think we can all contribute, and we can all offer our help to industry partners if they have questions. I think that's what we can do in the universities, and maybe that's also one small step towards using those models. I don't know if that answers the question.
No, that's okay. Interesting perspective. So now we can pass to the next one. Is this, unlike 10 years ago, we now have more computational capabilities. What are the major challenges for applying 3D constitutive models that include the intermediate effective stress to numerical simulation in geotechnical engineering?
But that's a question that is related to any model. If you mean 3D compared to 2D simulations, or it's a question of computation time. But I think I did not quite understand the question.
Okay, it's more which challenges have you seen in applying these 3D constitutive models?
Okay. I mean, every model should be, every constitutive model is in fact 3D, because a stress state in some mechanics is 3D anyway, and it's not 2D. But you can idealize at least plane strain predictions, but you will have a 3D stress state anyway. But if you model 3D instead of 2D, you will have issues like computational time. And for example, our industry partner, he said they don't have time to wait for that long, because that does not work in industry. So they say they have to reduce computational time. That's why they often idealize a problem plane strain, even though they know it would be better to do it as a 3-dimensional simulation.
Thank you, Doctor. We have 2 more questions. As an engineer, what do you think has been your biggest challenge?
What has been, sorry, which challenge?
As an engineer, you in your case, what do you think has been your biggest challenge?
What has been my biggest challenge? Maybe the PhD thesis. I don't know. I mean, I maybe to decide to. I really liked working on my PhD thesis with every year, but at the beginning I was not sure if this topic of hypoplasticity will be my topic. But so the first year of my PhD thesis was probably the hardest, because after that I loved the topic and things were fine. But the beginning, I was a bit unsure, and with all those tensor equations, and I was not sure if I'm the right person for that. And as I really enjoyed it, it was very much fun. But the first year was maybe the most challenging one, I would say, or the first 2 years. Yeah.
Thank you. We have questions from the audience too. If you let me, I can ask you.
There is, I think, this is in Spanish. I don't understand that. But there was a question as well.
We have
I knew I wish there was a unified tool for all the topics that you presented to the use of students and teachers. I would like to know if there is a current goal or not yet planned. You mean to, yeah, there was a time where I had this small project. I was working on this animating soil models. I would like to continue, but currently, or also probably the next years, I'm involved in some other projects. But on the long run, I really would like to continue because it was not a huge project, but compared to my research, people are much more interested in that teaching project than they are in my hyperplastic papers. So I think I really want to continue, but currently I won't continue because of but I'm thinking about applying for funding in educational to continue with this educational tool, but I don't have any current plans about that. But yeah.
Okay, I'm about to read the next one.
Yeah. Yeah, no, son.
You.
Yeah. Maybe you.
Okay.
I'm laughing because I mean that's definitely important because quite some people ask about no-sand. I have never worked with this model. Of course, I could do that and get into it. As I'm currently not working, I have some other things that I started and I also want to finish, but I definitely have this model on my list because you're not the first person asking for that. So this seems to be of interest for the community. And in fact, during this project, I had some ideas, but I had completely different ideas than what I showed. And there were some students writing, "Oh, could you add Mises as well? Because I want, that would be great." And then I thought, okay, they want to have Mises. So I was very grateful for feedback from lecturers and from students because that helped me to, and there were so many nice ideas. I could not do half of them, but no-sand is on the list. But as I said before, I'm currently not working on this project anymore. But yeah, it's definitely important because people ask for that.
We can pass to the next one, which say animation helps to better understand concepts such as constitutive models and critical states.
We missed one. Unlike 10 years ago, we now have more computational capabilities. Ah, yeah, you asked that before. What are the major challenges for applying in a three-dimensional engineering? Yeah, we talked about that. Okay, and probably this question, you also were talking about these advanced constitutive models and not only like basic models. And yeah, you have issues with computational time, you have issues with convergence problems as well. And yeah. And on this website, Soil Models as well, there is a forum as well. So every user can post and ask questions, and there are other users that can answer and help because people tend to have the same problems, and so it makes sense to help each other. What other concepts do you think that can be treated as animations that it can be better understood? I think many. I think it depends. Some people, I also talk to some people, they say, well, I'm fine with tensor equations. I don't need your 3D plots. And they're abstract thinkers. They don't need animations or visualizations at all. But if you are a person that needs visual explanations, and I'm very much a person that needs visual explanations as well, then I think you can basically animate everything. Yeah, you can. I think, yeah. I think there's still a lot to animate.
We have we have the next one, which say he's a student who is beginning to study the soil constitutive models. So I think your animations can help for all the youth texts. My question is very simple. Based on your experience, what are the readings books that you highly recommend to a better understand to the soil constitutive models?
I think there are two books I highly recommend, and they're normally, I just changed the office. Normally they're always lying on my table, but I changed this week. I got a new office. It's both books by David Muir Wood. The one is Soil Mechanics and Critical State Soil Mechanics, and the other one is Geotechnical Modeling by David Muir Wood. And I think based on those two books, I learned soil constitutive modeling, and I can highly recommend those two books. But there are definitely other books as well. And there is one by Ortigao. It's more about critical state soil mechanics, but it also helps to understand the models. If it's just about constitutive modeling, then it's geotechnical modeling by David Muir Wood. He starts with very basic linear elastic models, perfectly plastic models, and then also the modified chemical model and so on. So I think those three books, I highly recommend it.
Thank you, Doctor, for your recommendation. We have this one which says, thank you very much for the presentation. It was very interesting. And the question is this: MCC and clay plasticity fit well in clays, but what about on mixed grain soils? Have you ever used them or any such soils?
I have used clay hypoplasticity for a silt called Dresden clay, but it is a sandy silt, and because there is at least for hypoplasticity, there is a sand model and there is a clay model, and the one very nice goal would be that you have a unified model and you don't need to model, you just have different set of parameters. But so far, at least for hypoplasticity, this is not available. So for some mixed grain soils, you probably have to try out which model fits better, the sand hypoplastic model or the clay hypoplastic model. But I have worked with a sandy silt, and that worked well with clay hypoplasticity. But that's also a very good point. The plan in my PhD thesis was to create a unified model for sand and clay, but of course I failed. And but that's, you have to try it out. You have to try to calibrate a clay model for let's say sandy silt, or a sand model, and then you will find out if it works. But I did it, and it worked quite well for this special sandy silt.
Thank you for sharing this experience. We have this one question. We said another extra question. What languages do you use on those adult animations?
For the animations, for some animations, I made it very simple. I just I have all those. I implemented the constitutive models of clay hypoplasticity or modified chemical model in MATLAB scripts. And from MATLAB, I created individual, PNG or PDF plots. And then I just created a lot of them and put them together. What I used as well, I don't know if you're familiar with LaTeX. It's called a package called TIX and PGF plots. If you have a data files of an animation of a simulation, you can also do simulations using TIX and PGF plots. And I have done those modified chemical simulations with TIX and PGF plots. And there it's very nice. You can just directly or export the PDF animation. Yeah. Mm.
Thank you, Doctor. We have this last question for you, which say, what would you recommend to civil engineering students who wish to specialize the same as you did?
If I would recommend the same specialization, Yes, of course I would. I think it's a very, very interesting field, and I really like to work in the field of constitutive modeling. And even though I'm not in industry, so you definitely have to talk with people from industry, but I think they need people who have worked with constitutive models and who can do simulations. And I think but there are many fields where industry is searching for engineers. So if you're interested, I can recommend it because it's just my favorite topic. But yeah.
Thank you so much.
And you can use it after university, hopefully. Yeah.
This was a very interesting topic. Thank you very much, engineer, for your excellent presentation once again. All the members of GeoUPC student chapter are grateful for you for agreeing to share your valuable experience and teaching it with us. On the other hand, we want to leave you with the invitation to participate in future conferences with us. And we are pretty sure that we all know more about this topic, and we're about to follow it because it was really interesting and new for us. We thank you again for brilliant participation, supporting us in this Congress, and we wish you the best success and many blessings. If you would like to share so many goodbye words, we are all ears to hear you.
Yeah, thank you. Thank you once again. I think I was a bit too quick because I would have more time. But no, I thank you for the invitation. And I also want to congratulate you because I saw the other lectures and other presentations, and you were able to create such an interesting conference. And yeah, so well done, and keep on, and congratulations to that.
Thank you so much, Doctor. We have plenty of knowledge now because of you and your experience that you have shared with us. And we are pretty sure that you exceeded these expectations from the public. You have the claps on here.
Thank you. Yeah, thank you. Thank you. And I haven't seen who joined the presentation, but it was quite some people. So thank you, everyone. It's very nice that you kept listening and didn't escape after some minutes. Thank you and have a nice conference.
Thank you so much. If you would like to stay to the next one, which is coming.
Yes, I would like to stay. You just unmute me because I will stay. Yeah, that's perfect.
Yeah, that's perfect. It says you can stay on here, and you can see the chat which says thank you so much. You have a lot of claps. It was brilliant for you.
Wonderful. Thank you.
Thank you, Doctor.
Thank you. Yeah, and I just close the video and stay in the conference. Yeah, that's perfect. Thank you very much. So
thank you so much, Sandra. If you would like to say something.
Thank you.
Thank you, Doctor. Have a nice day.
Thank you, and see you later.